kind of problems in Chapter 3 where they were kicked, flicked, and pushed, where they were a horizontal launch projectile. But here we get to ignore bunches of stuff, which is awesome, and solve it an easier way. So VI for the glasses is 15.0 meters per second. And what we want to know is VF. And we know that the bird is, or the glasses are, 3.0 meters up. So what we are aware of is that final mechanical energy is equal to initial mechanical energy, final gravitational potential energy plus final kinetic energy is equal to initial gravitational energy plus initial gravitational. Great. So we know that the final gravitational potential is 0 because it hits the ground, so it can't fall any further. So 1/2 mvf squared is equal to mass gravity times initial height plus 1/2 mvi squared. One mistake I did see was people were thinking that it had an initial 0 velocity. It doesn't. It does have an initial velocity, so you can't get rid of that. But we're going to go ahead and solve for VF. So VF is equal to, I'm going to do this all in one step if that's okay with you. So I divided both sides by m by 1/2 m, took the square root of both sides. What I have is VF equals mghi plus 1/2 mvi squared over 1/2 m, and of course magically our m's go away. And then we can take that 1/2, we can multiply the whole darned thing by 2, which gets us the square root of 2ghi plus vi squared. And that gets us a raw answer of, drumroll, 16.84. You guys are the best. 8414 meters per second. And with sig figs, it should be 16.8. You have 3 sig figs there. You do? Yeah, you do. Okay, so 16.8 or 17 if you used mass, because then it would count against your sig figs. I'm rolling my eyes. Simplify, 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 simplify. Okay, lots of people got this one right. These are fairly straightforward. Okay, if you didn't get it right, do you see where your problem was? Things like I had people who assumed there was no initial velocity. That would cause a problem. Okay. Next. Okay, so we have a insane backyard rope swing. It's 30 meters long because clearly your backyard has a cliff and you're going to swing out into a giant chasm and, won't the neighbors be surprised? You're starting off, yes, over a ravine, inclined at an angle of 37 degrees with the vertical. What we want to know is what is your speed when you get to the bottom of the arc? If you push off with a speed of 4.0 meters per second. So this has got to be like a rope swing out over a gorge or something, or a lake. This is just like the swing problem that was in your homework. What we have to do is get this distance. I cannot draw a little bracket today to save my life. There we go. We have to get that distance because that's going to give us the height. So this is just a mechanical energy problem. Okay, so we know that gravitational potential energy final plus kinetic energy final is going to equal initial gravitational potential energy and initial kinetic energy. What we further know is that at the end, at the bottom of this swing, you can't fall any further unless you let go of the rope, but we're not going there. On the swing, you can't fall any further, so you have 0 gravitational potential energy. You're at the bottom of the arc. So that means that 1/2 mass velocity final squared equals mass gravity height initial plus 1/2 mass velocity initial squared. Gee, this is looking an awful lot like the last problem. So solving for VF, we get the square root, and I'm going to shortcut to the real solve, 2 times gravity height initial plus VI squared. It is the same exact algebra that we did here. hence why I'm shortcutting. Now, the problem becomes, how do we figure out the height? Well, the height is the difference between this elevation and this elevation. So to do that, we have to figure out this length, and we can do that using a trig function. So we know that the cosine of 37 is the adjacent side, which is the side we're interested in, over the hypotenuse, which is our 30 meters. So that's 30.0 meters. So cosine of 37 times 30.0 meters will give us the length of our adjacent side. Okay, so the 23.959 meters is actually your height at that point. It's this height. When you subtract that from 30 meters, you get the difference in elevation for this interval. In other words, basically how far you can fall. And it ends up being like 6.04 and some meters. Okay, yeah, on and on and on. What that gives you is a final velocity of 11 point, your raw is 5984, blah, 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 blah. Final velocity is 11.6 meters per second, and you do have 3 sig figs. Okay, so number 3, we've got this tricky situation where we have to determine which direction the box is moving. We know that the force of the puller is 234 newtons, and how would we determine if the box is moving up or down the ramp? We can do a sum of forces on the x. There's a problem with that, though. Why? The problem with that is friction. We don't know which way friction is going to be acting until we know which way the box is moving, because friction opposes motion. So if the box is moving up the ramp, friction is moving down the ramp. If the box is moving down the ramp, friction is pointing up the ramp. So you have to, I know, isn't it tricky? It's a great problem. Or dumb, potato, potato. So how would you determine if this box is being pulled up the ramp or pulling the person down the ramp? Which two forces would you compare?
Force of gravity and force applied.
Force of gravity and force applied. If you are applying more force than gravity is applying down the ramp, you win. If gravity is applying more force than you are applying up the ramp, gravity wins. So, who wins? Gravity, hands down. This poor schmuck is getting pulled right down the ramp, kicking and screaming. It's a low friction surface. Well, yeah, and here's the further tricky part, which we don't really address here because we simplify things. If this was a high friction surface and the force applied and the force of gravity were close, we could have some debate, but they're not even close. It's a clear win for gravity. Gravity's applying like nearly 2.5 times as much force as the puller. Gravity is dragging this guy or this gal, this person, right down the road, right down the ramp. So let's do that comparison real quick. Yes, absolutely. So let me I forgot to hit pause. So it is negative work. The puller's activity, is it slowing down the travel of the box? Would the box go faster if the puller just let go of it? Yeah, it would. So they're doing negative work on it. They are reducing the velocity. They are reducing the motion of the box. How do we know if it's 0 or 180? You look at the motion of the object. Well, ouch, ow, because the distance is down the ramp, and that would be Cartesian negative, and so if you have a negative distance, but you still have cosine of 180, then it would be positive work. Oh, this hurts. Which actually it might be positive work because the motion is negative, and so the work is opposing the motion. That's the thing. The work of the puller is opposing the motion.
But your distance would be just a distance, so it's positive. If you did your negative work, then you wouldn't have cosine 180 just be 0.
True.
Because you're
True.
negative on this side. So.
True. Yeah, okay. It's still negative work because it's in opposition to the motion. Okay. So the cosine 0, cosine 180 thing is really just about, is this force in the same direction as the motion, or is it in the opposite direction of the motion? If the force that we're talking about that's being applied is opposing the motion, you know, if that's the motion and this is the force, then the angle between the two of them, and remember they're vectors, you can move them like this, the angle between those two is 180, okay? If the motion is in the same direction as the force, then the angle is 0, okay? Okay, so that's part A. Let's do part B. Whoops. Okay, part B. Work done by friction is equal to the force of friction times cosine theta d. Here we have to do, you know, the mu k mg cosine 15, and what we end up with, and I'm just going to go ahead and put that in, is 236.89 blah blah blah. Again, this is going to be cosine 180 because the friction is opposing the motion. Now, friction always opposes motion. Whether the box is sliding up the ramp or down the ramp, the friction would oppose the motion of the box because friction always opposes motion. So that times cosine 180 times your 7.5 meters, and what we get as a raw answer is shockingly close to the work done by the puller. Shocking. 99 blah 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 joules. And our raw answer, that's our raw answer. Our final answer for work done by friction would be negative 1800 joules. Again, the friction is retarding the motion of the object. It's slowing it down. It would go faster if we covered the slide in Crisco. It would go a whole lot faster. Okay, so you have two options for C. You can either add up all the works to get your net work, or you can do net work equals net force times cosine theta d. If you are doing net work cosine theta d, the object is going to be moving in the direction of the net force. Always. So it's cosine 0. So you can really pretty much ignore that. I took what I considered to be the easier path, which was doing the net force, because I hadn't done work done by gravity. I had done force of gravity, I had done force of the puller, and I had done force of friction, but I hadn't done the work done by any of those. So I went ahead and went with the net force because I had all those.
If you're doing work,
Mm-hmm.
the way you have the picture drawn is kind of confusing me. Friction
Is upslope.
is upslope, so why do you have it as negative? Because I got it as negative.
Well,
That was assuming that it was in the other direction.
because you're okay, so that was the conversation we had a little bit ago. Can we hold that conversation? Because it's a very good question, but let's walk through this first, okay? So what I did was take the 234 newtons plus the 236.8 blah blah blah, which is the frictional force, and these are both up. I added to those the 634.7 blah 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 newtons downward, which is the work done by, or the force of gravity, and then multiplied that by 7.5. For my net force, I got 163.86 newtons down slope. It is moving at cosine 0. Now here's the thing, the net work, this is where we run into issues with the positive negative, I guess. It does. So we've got a net force downwards times 7.5 meters. The magnitude of the work is 1,200 joules. It's like 1,228.9, etc., 9 and change. So it comes out to 1,200 joules. Now, is that work positive or negative? Well, it is down a slope. This is true. but that work is increasing the velocity of an object. It is moving an object. So I'm going to fudge and say the magnitude of the work is 1,200 joules. Typically, if the work is in the same direction as the force, we call it a positive. We'll talk more tomorrow, and then we'll get ready for a mixed FIP. I would like to grade homework. Maybe we can grade homework tomorrow? Maybe we can do that?
Friday.
You have 2 questions? We can do it Friday, but we gotta, okay, we'll grade homework Friday to get that on this 9 weeks.
Is that 160